残酷な天使のように少年よ神話になれ。青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなた。そっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょう。その背中には遥か未来目指すための羽があること。残酷な天使の手で窓辺からやがて飛び立つ。ほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ。
Calculus. All right, everyone, we're back at it. We're talking a little bit about graphing functions today. Using the tools we've picked up so far in calculus, we will find that our ability to graph functions has been greatly enhanced. So we've got a comprehensive set of tools that will let us graph functions really well. Now, let's stop for a second before we go too far and let's just even talk about graphing functions. There's not really any reason other than a math class why you have to graph a function by hand nowadays. None at all. Totally useless in terms of having to produce graphs of functions. In terms of understanding mathematics, very useful. So, the main thing we're going to focus on here is not the specific techniques to graph a function. If you go to work and your boss asks you for graph these numbers, Bill, and you throw him a hand-drawn graph, he's going to laugh you out of the room. Use software. This is why we have computers. This is definitely the reason that we have these, or this is one of the main benefits that technology offers, is the ability to rapidly produce visualizations of data without great effort. So we'll focus on the intuition, the theoretical components of graphing functions, and the way that that helps us. You know, we have powerful graphing utilities. It's not really a real-world skill anymore, but understanding how to graph functions and getting familiarity with the general shape of functions, the information encoded in functions. This is a powerful, powerful driver of intuition in mathematics. So, without much more to do, let's get into it. Okay, guys, so we're going to start out just with a set of guidelines. This is a bit more exhaustive than is necessary. You certainly don't have to do all of these steps every time you graph a function, but it's a very useful way to think about the process. It's a good guideline. It's a good set of guidelines. So you don't have to do this every time. This isn't, nearly the type of depth you need to do to graph most functions, but if you want to sketch a good graph by hand, it's worth at least talking about how you do it. So let's run through. Step number 1. Identify the domain or interval of interest. On what intervals should the function be graphed? It may be the domain of the function or some subset of the domain. Basically, we just want to figure out where we're even supposed to be looking. All right, step 2. Exploit symmetry. Take advantage of symmetry. It can save you a lot of time when you're graphing a function. For example, is the function even? I.e., is it true that f of minus x is equal to f of x? Is it symmetric about the y-axis? Or is the function odd? Is the symmetry mirrored across the y-axis? i.e., is f of minus x equal to minus f of x? The function's neither even nor odd, we might not be able to do this. However, if it's even or odd on part of its domain, if we have some amount of symmetry, we could at least exploit that. All right, step 3. Find the first and second derivatives of the function. We need the first and second derivatives to determine extreme values, to determine intervals of concavity, to determine inflection points, intervals of increase and decrease, all of these things, all the stuff we've been talking about. So, however, occasionally, computing derivatives, particularly in a lot of cases second derivatives, might not always be practical. Sometimes these guys can be some real beasts. So sometimes you'll have to go without this. Sometimes you'll have to just do your best without the rest of the derivatives there. But in general, if you were persistent enough, you can still do it. All right, step 4. Find critical points and possible inflection points. Determine the points at which f prime of x is equal to 0, or f prime is undefined. Find the critical points of the function. Now, after that, you'll want to find the places that are candidates for inflection points. Another way to think of this is you'll want to find the critical points of the first derivative instead of the original function. That is, we'll want to determine points at which the second derivative is 0 or is undefined. So once we got these guys, we'll be ready to go on to step 5. Find intervals on which the function is increasing or decreasing, and the intervals where the function is concave up or concave down. This is probably the most important step for figuring out what your graph is actually going to look like. We'll talk about this a lot more later. So, the first derivative, if you recall, determines the intervals of increase and decrease, while the second derivative determines the intervals on which the function is either concave up or concave down. Between the first and the second derivative, we get all this. Cool. Step 6. Identify extreme values and inflection points. Now, we'll use either the first or the second derivative test to classify our critical points. Now, when we go through and we do this, we'll want to take both the x and y coordinates for the maxima, minima, and inflection points. Really, we just need the x coordinates. The y coordinates come for free just by plugging it on into the function. It might take a little bit of arithmetic, a little bit of extra calculation, but there's no theoretical new stuff that we need. We just need to run it on through the function. Cool. And that takes us to step 7. Locate all asymptotes and determine the end behavior of your function. So now we're going back a little bit here. This is from a bit earlier in the class. We got to find where the vertical asymptotes are at. If we're dealing with a rational function, this is frequently the zeros of the denominator of the function. And then we'll want to find horizontal asymptotes. You can do this for any function. You can find horizontal asymptotes for any old function. You just want to look at the limits as x goes to either positive infinity or negative infinity. Sometimes you can compute both of these at once if your function is particularly well behaved. A lot of the times you'll have to do them separately. This will tell you what the function does in the limit. This will help you graph your end behavior. Make sure the tails of your graph are pointing in the right way. Step 8. Find the intercepts. Now that we've done all this other stuff, let's find the intercepts. So, the y-intercept of the graph is found by setting x equal to 0 and evaluating your function. This will give you an xy coordinate. It'll let you know when, if ever, your function passes through the y-axis. Now, when I say if ever, that's for the cases where your function may not be defined at 0. If your function is not defined at 0, then you will not get a y-intercept. So don't always expect to find one. However, if your function is defined at 0, if you can plug 0 in, you got a y-intercept, pal. All right, then we want to find the x-intercepts. Once again, your function does not have to have x-intercepts. But if it does, you find them by setting y equal to 0. That is, you're going to solve and see when your function is 0. You're going to find the values of x such that f of x is equal to 0. These are the roots, the real zeros of your function. Okay, cool. Once we got these guys, we can plot them on a graph. Great. Time for step 9. Choose an appropriate graphing window and plot the graph. So looking at all the stuff we did in the previous steps, let's start to graph our function. If you're using graphing software, you're going to want to check for consistency with your analytic work, although in general, the computer's going to do it right. And no matter what you're doing, you should always be double checking. Is your graph complete? That is, does it show all of the essential details of your function? Have you shown enough that any viewer can get a reasonable sense of what's going on with this function? If you have, congratulations, you're done. Let's do some examples. Oh man, guys, example time. Boy howdy, example 12. Given the following information about the first and second derivatives of a function f that is continuous on the open interval from negative infinity to infinity, so for all real numbers, let's sketch a possible graph of f. So we've got a whole bunch of information down here. We've got a bunch of information about the sign of the first and the second derivative on a lot of different intervals. So let's try to make this a little bit more manageable. I'm going to start out just by making myself a little chart, okay? I'm going to start out just by taking what amounts to a number line right now. So I'm going to make myself a little number line. And then I'm going to take each one of these points that appears in an interval, sans the infinities and negative infinities, and I'm going to put them on here. It doesn't matter if I'm not evenly spacing them yet. All this is for is a heuristic to help us get organized. So I'm going to look for the smallest value I see in one of these intervals endpoints. From what I'm looking at, I got 0, 2, 3, 1, 3, 4, 1, 2, 4. Looks like 0 is the smallest. So I'm going to throw a 0 right on there. All right, next biggest. Looks like that's 1. All right, I'm going to throw a 1 in here. Nice. Next biggest looks like it's a 2. All right, and then I got a 3. Yep. And it looks like my biggest is a 4. And then after that, we got our infinities, negative and positive. All right, so what I'm going to do now is I'm going to make myself something like a chart. So I'm going to just get organized real quick here, draw myself a little bit of a sideways T thing, just like this. I'm going to write F prime right here and F double prime. I'm going to go on down and make myself, oops, let's make that a little bit cleaner. Let's see, I'm going to make myself some lines, separate my table up into chunks according to these numbers, the cutoffs, the endpoints of each interval. And then what I'm going to do is I'm just going to record the signs. So I'm making a full little chart right here. It's going to be great. It's going to be wonderful. You're going to love it. And we're going to learn a lot about what this function's graph looks like. Gosh, this is a messy chart. Let's fix it up a little bit. Okay. So I'm going to just go through here and fix this up a little bit. But the idea is that we're going to record the first and the second derivative sign on each interval. And then from that, we're going to sketch a general picture of the shape of the function on that interval. Then we'll just be able to glue these guys together and build ourselves a pretty nice general idea of what the function's graph looks like. Cool. Let's try it. Let's get into it and let's start recording information. So from negative infinity up to 0, that's this first guy right here. Okay, I've got f prime is less than 0. I'm going to put a negative in there, and f double prime is greater than 0. That's a positive. All right, cool. Done with that guy. Now we're looking from 0 up to 1. That's this guy right here. Okay, so f prime is greater than 0. Cool. I'm going to put a plus there for positive, bigger than 0. And f double prime is also greater than 0. I'm going to put a plus there, positive. Done. Just going to go through piece by piece with the rest of them. Now 1, 2, I've got f prime greater than 0, positive, f double prime less than 0, negative. Done. Okay, f prime greater than 0, f double prime, f prime less than 0, f double prime greater, less than 0 as well on the open interval from 2 to 3. Okay, negative, negative. F prime less than 0, f double prime greater than 0. So we got negative, positive. Bam. F prime greater than 0, f double prime greater than 0. Positive, positive. Bam. Okay, so we recorded all this data. Now, let's just scroll down a little bit here, because this is really everything we need, except for that continuity assumption. That actually matters a little bit. But just off to the side real quick here, let's make ourselves sort of a table of what can happen. The basic idea is just that there's only so many possible combinations of signs that we can have with the first and the second derivative. So I'm going to make myself a quick little chart here. I'll do this in a different color just to keep everything organized. I'm going to put f prime, I'm going to put f double prime. This is not part of our answer. This is just a little bit of extra stuff for us to get an idea of what we should expect to see at the end of the day. So I'm going to make this into a little table, just sort of like an answer bank down here, yeah? This is just for us to make this a little bit easier. Bam. All right, so we got f prime, we got f double prime. I'm actually going to draw in some little lines here. And then I'm going to, at the bottom, in the last column, this is where we're going to get our shape. This is the shape of the graph. So here are the possible combinations. We could have both of them positive. We could have f prime positive and f double prime negative. We could have f prime negative and f double prime positive. Or we could have both of them negative. Let me give ourselves a little bit more room. There we go, a little bit better. Cool. So all we're going to do now is we're going to sketch the general shape of the function in each of these situations. And this is true for any old function pretty much. So when f prime is positive and f double prime is positive, we look like a cup facing up, and it's the part that's not going down, it's the part that's going up. So it's the right half of a cup facing up. Now when f prime is positive and f double prime is negative, it's like a cup facing down, and it's the part that's increasing, just like that. When f prime is negative and f double prime is positive, it's the decreasing part of a cup facing up. And finally, when f prime is negative and f double prime is negative, we're a cup facing down and we're the decreasing part of that. So concave up and concave down, and whether we're increasing or decreasing, basically says, oh, here are the 4 basic types of shapes that can occur in a nice function, in a function with 2 continuous derivatives, a C2 function, twice continuously differentiable. Don't worry about that terminology, but that's just the general gist of what we're doing here. We're giving ourselves something like a answer bank, yeah? Okay, giving ourselves a little bit of an idea of what could happen. All right, this table is a bit messy, but that's fine. We're just going to sketch which one of these our function is on each of these little intervals. So it's pretty much just fill in the blank. I see negative, positive, negative, positive. So I got this shape right here. And then I got positive, positive. Then I have this shape right here. And then I have positive, negative. I got this guy right here. Okay, negative, negative. That's this guy right there. Last entry in that table down low. Then I have negative, positive, second to last entry. Just like this. Oh, messy. There we go, a little bit better. And then positive, positive, something like this. Now all we have to do is sort of glue it together. There's no more information it's really giving us other than that our function is continuous. So if we just make ourselves a quick XY axis, we can pretty much get a good idea of what this function's doing. So kind of messy XY axis, but good enough. All right, easy, easy. So now we'll take all this info we got up here, all of these points, and actually, now that I think of it, I should probably make this a little bit more like this graph here. Oops. Yeah, whatever. Good enough. Bam, 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 bam. Here we got 0. Actually, I'm going to even make this a tad bit longer, just so we have enough room to show everything just right. We got 0 right in here. Then we got 1, 2, 3, and 4. We should always label these so we know the scale we're working at. Perfect. Now we just have to take these little pieces and connect them together properly. So I'm going to switch to a different color now. I'm going to give us a nice orange. There we go. And we're just going to hook all these guys together. So we look like this shape to the left of 0. And the nice thing is we can stretch this guy out a little bit vertically and stuff like that. Won't hurt anything. So let's just kind of go in like this. There we go. Why not? Good enough. Okay. Now afterwards, we're going to look like this shape. This cup going up. Okay, so I'm going to try that out, and I don't have to do it for very long. I'm going to make it relatively symmetric, just like that. Bam, it's just going up from 1, yeah? This is where it switches from being a cup going down to a cup going up. And then right afterwards, between 1 and 2, I am like this shape. Bam. Okay, and that's at 2. Neato. And then afterwards, between 2 and 3, I'm going down. I'm going to make this relatively extreme. Just for fun, just to showcase that we can mess around with the scale a bit. Okay, and then from 3 on over to 4, looks like I'm, so let me make sure I got this pretty smooth. Oops. Make that a little bit better. Let's see. Always tough to graph these bad boys. Okay, and then at 4 afterwards, I'm back to being up. Bam. Okay, kind of messy. I think I have a better graph actually done with a computer like we always should do down below. But let's see how well this guy matches up to it. Let's go check it out. Okay guys, I'm back with a better graph, one made by a computer, pretty close to the one we just drew. Looks about the same, but notice this is all we're doing. We're putting together little pieces. They just look like chunks of a parabola. If you've ever noticed, chunks of a parabola are pretty much telling us exactly what all of these nice enough functions look like. All of them are just glued together little chunks of a parabola, pretty much. Whether it's this guy or this guy, doesn't matter. We're just either looking at the left half or the right half, and we're taking a piece from each. That is, we're taking this guy, we're taking this guy, we're taking that guy, and we're taking that guy, and we're just gluing them together, piece by piece by piece. So we got this guy right there, that's this one. And then when we look at this guy right here, that's the one next to it. And, this one over here, it's that guy again. This one is that guy, so on and so on. See what I'm saying? It's just these couple of shapes. There's not too many we even have to worry about. It's just a few different basic shapes, and that is enough to give you all of these nice functions graphs. Cool. If you want to see it slightly better organized than what we just did up top, this is the kind of chart that I'm sort of trying to draw when we were looking at things before. We're looking at the behavior of f. Is it decreasing or increasing? Is it concave up or is it concave down? Luckily, since all this information is given just by the sign of the first and the second derivative, our chart before with pluses and minuses is just a quicker way of writing this information. So we're just splitting it up on the intervals that we have, and we're figuring out which chunks we're gluing together. Now, the names, when we transition from the chunks, are just the definitions we've been talking about so far. When I turn from this little chunk, this L-shaped chunk right here, into this upwards L-shaped chunk, that's called a minimum. When I change from this L-shaped chunk, or R-shaped chunk, to this R-shaped chunk, that's called a maximum. When I change from a forward or backward L to a forward or backward R, those are called inflection points. And so on. It's kind of smooth, yeah? Kind of neat.
Look at this graph.
おめでとう